Thank you. So hello, everybody, and hello, Philippe. I'm very honored and happy to be invited to celebrate your birthday. And I'm sorry I could not come in person. So yes, at such an occasion, one starts thinking back to find out when we met for the first time. And I was a bit overwhelmed when I realized that it's actually exactly 30 years ago this year, in 1994, when I came as a postdoc to Saclay. And I remember that at that point, I was very impressed that you actually had Kristjansen and Philippe walking around in person and not just their famous textbooks standing on the shelves. And I'm sure that the postdocs who came just slightly later than me, they felt exactly about the same about you, Philippe, and your great iconic yellow book on conformal field theory. That book is certainly a classical and iconic reference for any theoretical physicist today, and I'm sure it will remain so for many decades. And yeah, of course, you also did many other important contributions to physics. So during my postdoc at Saclay, we actually did not collaborate, but we had a collaboration about 5-10 years later, where we worked on causal dynamical triangulations, and where I had the privilege to experience your very sharp and fast way of thinking. In recent years, we've not met so often, but I think our research interests have always been somewhat aligned. So today, I will not speak about causal dynamical triangulations, but I've chosen something more recent that I hope could also have your interest, namely integrable monopoles. And this work is based on a paper I wrote with Kristjansen and also on some work in progress. And by monopoles, I mean magnetic monopoles. So one can, of course, ask oneself why one should worry about magnetic monopoles. And in this connection, I cannot resist mentioning the following citation from Joe Polchinski, who said that the existence of magnetic monopoles seems to be one of the safest bets that one can make about physics not yet seen. This is a statement he made at the Dirac Centennial Symposium about 25 years ago. And we, of course, all know that magnetic monopoles have still not been found, but there is actually an experiment at CERN, the Medal experiment, which is looking for such objects. So what I will consider today is actually a 4-dimensional quantum field theory, which contains both a monopole and a Higgs particle. And I think this is the closest I will ever come to give a talk having some experimental relation. But the relation to experiments also stops here, because the theory I will be considering is a supersymmetric one. More precisely, I will introduce a monopole in n=4 super-Yang-Mills theory. And my motivation for doing that is that this will provide us with a novel example of a supersymmetric defect conformal field theory, which is also integrable. It's integrable in the sense that its one-point functions are computable in closed form. And the defect is simply the word line of a magnetic monopole, which is obviously one-dimensional. So our defect CFT is one of codimension 3. Another motivation for studying that setup is that it might teach us something new on S-duality. So n=4 super-Yang-Mills has a duality known as S-duality, which is a magnetic electric duality, under which the word line of a magnetic monopole, which is called a 't Hooft line, is mapped to a Wilson line. So if we can solve exactly the 't Hooft line setup, then we might learn something about Wilson lines and different phases of space theory. Okay. So the plan of my talk is first to introduce this monopole Higgs configuration, and then move on to explain how one quantizes the theory in the monopole background. And the quantization in the monopole background, it involves some very beautiful and exactly solvable quantum mechanical problems. And once you've done that quantization, of course, you have the full perturbative program that allows you to compute, in principle, any correlation function of the theory. And I will concentrate on one-point functions, which you can actually compute in closed form. And I will finish by some conclusions. Okay. So a magnetic monopole is a point-like object which gives rise to a magnetic field which is radial and looks like this. And here I use conventions where I set all the constants of nature, including the electric charge, equal to 1. And with that convention, this quantity B here has to be integer. We know that, as shown by Dirac, that if magnetic monopoles exist, then the product of the monopole charge and the electric charge has to be quantized. That's the Dirac quantization condition, which dates back to 1931. Okay, I will, as I said, consider a magnetic monopole, and I will consider one which is simply static at the origin, and its world line then just extends in the time direction. In the quantum field theory language, the way one describes a monopole is via a disorder operator. It's an operator which simply prescribes a certain singular behavior of the gauge field, and then you have to perform the path integral with those conditions as boundary conditions. And for a magnetic monopole, you can take the gauge field to have the form given here in spherical coordinates. So you see it's singular at theta equals pi, but not at theta equals 0. So there is a half line of singularities. But as we all know, and which was understood a long time ago, you can choose another value for the gauge potential, which is regular at theta equals pi, but not regular at theta equals 0. And then the two have to be connected by a gauge transformation in the region where they're both well defined. And that is one way of getting the Dirac quantization condition. Okay, that was everything, something which was understood a long time ago. Now I want to introduce the monopole in n equals 4 super Young-Mills. And of course, n equals 4 super Young-Mills is a non-abelian gauge theory. So my A field is not just a number, it's in general n by n matrix. And I have to put some matrix field B here in front of my A field. And I will, as I said, not only introduce the magnetic monopole, but also an expectation value for one of the scalars in n equals 4 super Young-Mills. In n equals 4 super Young-Mills, there are 6 different scalars, and you can introduce a vacuum expectation value to the combination of them in a certain way. And if you do choose the parameters right, you can arrange that half of the supersymmetries of n equals 4 super Young-Mills are conserved. And to do that, you have to take the classical expectation value of the scalars to be given like here, where ni is some unit vector, 6-dimensional unit vector. And in the following, I will consider the simplest case where the B field is just a diagonal matrix with a 1 in the upper left-hand corner, and only one of the scalar fields has a vacuum expectation value different from 0. In general, I can choose B as any element of the Cartan of the gauge group, but choosing it like this, I assume the gauge group is UN. As I said, this configuration, it conserves half of the supersymmetries, and the setup constitutes a one-dimensional defect CFT, as conformal symmetry is conserved on the 't-Hooft line itself. And it's a defect CFT of codimension 3. Okay, so to quantize this system, well, we have to follow the textbooks, basically. So we have to expand around the classical fields, which in this case means the classical gauge field and the classical scalar. And due to the form of the classical fields, then the other fields of the theory, of which are both scalars and gauge fields and fermions, they have field components which behave differently depending on where in the matrix they appear. So field components of the type gamma are not affected by the monopole, also not the field component on the upper left-hand corner, and that's because all interactions appear via commutators. But the fields in the first column and the first row here, the beta fields, are heavily influenced by the monopole and get masses. So what we have to do is to expand around the classical fields and invert the quadratic part of the action as usual. after gauge fixing, of course. So what we have to do is to take our action, which I've written here in symbolic form with some inverse propagator d to the minus 1, and invert this operator d to the minus 1. And a way to do it is simply to find the eigenvalues and the eigenvectors of this operator, and then write the propagator as a sum over outer products of wave functions, and then 1 divided by the eigenvalue. That's a standard method, and this turns the quantization of the theory into a quantum mechanical problem. And this quantum mechanical problem turns out to be exactly solvable, and the solution very, very beautiful. Okay. So there are 3 types of fields whose quantization one has to worry about. There are the scalars which don't get a vacuum expectation value, the temporal component of the gauge field, and a ghost which results from gauge fixing. These all behave as scalar particles in a monopole potential. And the corresponding quantum mechanical problem was solved already by Dirac himself in 1931. For the fields who get a vacuum expectation value different from 0, there's one scalar and the vector part of the gauge field. There one has to study a scalar coupled to a spin 1 particle in the monopole potential. Now just a vector in a monopole potential as spin 1 particle, that was studied in the 90s by Olsen and others, and the solution was found. But as we will see, when we couple to this extra scalar, we actually get a much nicer solution, in fact, which I believe reflects the underlying integrability of n=4 Super-Yang-Mills itself. Similarly, for the fermions, we have a quantum mechanical problem, which is not the standard problem of a fermion in a monopole potential, but fermions in some non-standard monopole potential. And the non-standard part comes because in n=4 Super-Yang-Mills there's an interaction between the scalars and the fermions, and that gives an extra term in the monopole potential. So the standard case was solved in 1977 by Kasama et al. But again, you will see that this non-standard case is actually neater than the standard case and can be exactly solved. Okay. Let's start with the scalar in the monopole potential. For that, you have an operator that you need to invert, which is simply time derivative squared plus some Hamiltonian. And that Hamiltonian is exactly the quantum mechanical Hamiltonian, which describes a scalar particle in a monopole potential. And we can proceed to solve it in the standard way. You see it has a flavor of a particle in a central potential. So you solve it by separating the variables, you factor out some time dependence like this, and then you consider the radial and angular part in itself. And to diagonalize the remaining part, you introduce angular momentum operators, which commute with the Hamiltonian and which have standard SU2 commutation relations. They look almost like the standard angular momentum operators, but they have additional B-dependent terms. But still the problem can be solved and the eigenfunctions can be expressed in terms of spherical harmonics, not the usual spherical harmonics, but what is called monopole spherical harmonics. So the monopole spherical harmonics are indexed by some Q, which is the monopole charge, and in my normalization, it's simply B/2. So these monopole spherical harmonics, they have, as usual harmonics, an exponential part, and then they involve a polynomial of theta, which is not the standard Laguerre polynomials, but instead Jacobi polynomials. And the radial part is given in terms of Bessel functions, where J is an angular momentum. But here you see that we know already from representation theory that these quantities J and M, they have to be half integers or integers. But we see that due to this B/2 here, we learn that in this case, when the monopole is present, M actually has to be half integer. So a scalar is quantized. When a scalar is quantized in monopole potential, it has to have a half integer angular momentum. And we also see from this equation here, the direct quantization condition coming out, because if the wave function is to be single valued, then this quantity b has to be an integer. And it has to be single valued for a scalar, of course. You also see another interesting phenomenon, namely the phenomenon of spectral flow. Namely, if you start out, and that's the phenomenon that the spectrum depends on a certain external parameter. So if you start out with a B field which is 0, then of course the angular momentum has to be integer, and you have all the possible integer values in your spectrum. But if you then slowly change B to something non-integer, and this you can do of course only theoretically, then when you reach B equals 1, then the angular momentum is suddenly half integer. And if you continue to B equals 2, then the spectrum consists of integer values of the angular momentum again, and so on. And this is what is illustrated in this plot here. Here, the black dots and the single gray dots, they are constitute the spectrum when there's no magnetic monopole. And then if you introduce a magnetic monopole and let the B field vary between 0 and 1, then the spectrum flows as given by these black arrows here. So you see all states on the right-hand side move downwards, and all states on the left-hand side move upwards. And in that process, the lowest multiplet or singlet disappears. And then if you continue from B equals 1 to B equals 2, then the spectrum flows as given by the green arrows here. And again, the right-hand side moves down, the left-hand side moves up, and in this process, the lowest multiplet disappears. So at B equals 2, you have the spectrum on the right-hand side, where you start out with the L equals 1 multiplet. And in general, the spectrum starts out by an angular momentum, which is B over 2. Okay, this is something which has in principle been known for a while, but this was described in a very nice paper by Wilczek from 1982. Okay, so that was the scalars. And now having diagonalized this problem, you can of course move forward and write down what the propagator is in the monopole background for n equals 4 supernomials. And the way you do it is, as I explained, by spectral resummation. So you do an outer sum over a wave function, and you divide by the eigenvalue. And the eigenvalue is the sum of the temporal one and the rest, which appear here in the denominator. Then you have the time-dependent part of the wave function, the radius-dependent term, and then the angular-dependent term is encoded in the monopole spherical harmonics. This looks quite involved, but it can be simplified quite a lot. You can integrate over omega by contour integration, and there also exist formulas that allow you to sum over m. And if you do that, you end up with this nice expression for the propagator. Again, the angular dependence is encoded in a Jacobi polynomial, and the spatial and time dependence is encoded in a quantity which turns out to be an ADS propagator for an ADS space, which has the 't Hooft line as its boundary and the radial coordinate as its radius. This is, of course, somewhat how to be expected from the symmetries of the problem, but it's very neat to see it coming out in detail. Okay, so that completes the quantization of the scalar fields in the theory. Then let's move on to the gauge field. As I said, due to the fact that both the gauge field and one scalar has a vacuum expectation value different from 0, there's a coupling between the gauge field and the scalars. And the quantum mechanical problem that you have to solve takes this form here, where my matrix is actually a 4x4 matrix. So there's a 3x3 matrix in the lower right-hand corner, a row up here, and a column here to the left. And the way you solve it is by saying that you have a system with a scalar and a monopole potential. You know what the possible values of the angular momentum are. They are half integer. Then you add a particle with spin 1, and you expect that the good quantum number is the sum of the spin and the angular momentum from before. And that's indeed the case. So for my case of B equals 1, then I will have these possible values of the angular momentum in the first place, and I'm going to compose with the spins. I can do it in in 3 different ways. And in this case, you do a mode expansion, which is somewhat similar from before. The angular dependence for the scalar is again given in terms of monopole spherical harmonics. But for the gauge field, you need to use what is known as vector monopole spherical harmonics. So they are vectors, and there are 3 of them for a given value of the total angular momentum. And you construct them by combining usual spherical harmonics or usual monopole spherical harmonics with spin 1 representations. And that's what gives you the vectors. Then you have some mode expansion coefficients here, and the radial part you again assume is given by some Bessel functions with some index nu, which depends on the angular momentum. And now, for a given value of the total angular momentum, you have these 4 unknown constants and the unknown index of the Bessel function. And it turns out that these quantities are actually the eigenvalue or values and the eigenvectors of a 4x4 matrix, which is expressed in terms of 3J and 6J symbols. It looks very complicated, but it actually simplifies a lot when you start looking at it more carefully. So what you find is that these indices for the Bessel functions are actually given by some very neat values, namely J minus 1/2, J plus 3/2, and then a double degenerate case, which is J plus 1/2. And it's very interesting to contrast this to the case of a gauge field with no scalar coupling. In that case, there are of course only 3 values of nu. One of them is this J plus 1/2 again, but the 2 others are quite ugly values, which are not even rational numbers. So the fact that we couple this monopole to the scalar in the way dictated by n=4 super Yang-Mills actually makes the problem a lot simpler. And I think this is a manifestation of the underlying integrability of n=4 super Yang-Mills. Of course, I could also write down the eigenvectors, and they also do not look too bad. And I can find the propagators for these fields by spectral resummation. And again, they involve propagators in an auxiliary ADS2 space. A similar simplification happens for the fermions. So the fermion problem gets some additional term on top of the monopole potential. There's something coming from the interaction between scalars and fermions in n=4 super Yang-Mills. So one needs to solve an eigenvalue problem which has some additional terms compared to the usual monopole problem, namely these off-diagonal terms depending on the monopole charge. Again, you would do a mode expansion, and this time you use what is known as spinor spherical harmonics. There are 2 of them for each value of the total angular momentum. And in this way, in this case, the spatial dependence is a little bit more involved as before. You cannot assume to have the same functions in front of each of the spinor spherical harmonics. Now, if you solve the standard problem, you find again a solution, of course, in terms of these spinor spherical harmonics and some Bessel functions. But the Bessel functions, again, do not have very nice indices. They have these, in general, irrational values of the indices. But when you now couple to the scalar field as dictated by n=4 super Yang-Mills, suddenly these indices become nice integer numbers, namely J and J plus 1, where J is a total angular momentum. And again, I believe this is a reflection of the underlying supersymmetry or integrability of n=4 super Yang-Mills theory. Okay, so as I said, this defect CFT that we have now constructed and quantized is integrable in the sense that its one-point functions can be computed in closed form. And let me now turn to discussing that. It's clear that with the quantization in place, we can proceed to computing in principle any correlation function. But one-point functions are, of course, the simplest one, and they are non-vanishing because the translational symmetry is broken. Okay. So let me consider some generic local operator in n=4 super Yang-Mills built from scalars. It has to be a trace of something to ensure gauge invariance. And if I consider the lowest level in the large n expansion, then it's just a simple trace. And since I have 6 scalars in N-4 super mills, I can write a general local operator built from scalars in this way here, where psi are some components of a wave function. So such an operator is in general not a good conformal operator, but we do know how the good conformal operators look like. Namely, they can be characterized as eigenstates of an SO6 integrable spin chain. This is something which was understood in the seminal paper by Minahan and Rembe about 20 years ago. And the eigenstates of an integrable SO6 spin chain are in general characterized by 3 sets of beta roots or rapidities. And these then have to fulfill a set of algebraic beta equations. And if you have a set of roots which fulfill these algebraic beta equations, then you can reconstruct a good conformal operator of N=4 super young mills. Okay, in this language, you can write the one-point function of such a good conformal operator in a neat way. Namely, you can express it as an overlap of this beta eigenstate representing the operator and a boundary state representing the defect. So in this case, the boundary state that I have to take can be written in this form here. It's a general spin chain state or general scalar operator, and its wave function has some components which for a given combination of the scalar fields here are simply the corresponding components of the direction vector of the monopole. So here I have reinstated the general form of the orientation vector of the monopole. With that boundary state, one can express the one-point function as an overlap between the beta eigenstate and the boundary state. Then there are some quantum field theoretical factor in front, and we have to divide by the norm of the beta eigenstate. And this overlap does exactly what it's supposed to. It takes, for a given contribution to the beta wave function, it replaces a field by its scalar, its vacuum expectation value. And that's exactly what gives you the one-point function at tree level. Now, it's been understood in the recent years when such a boundary state is integrable, meaning that its overlap with the beta eigenstates can be computed in a closed form. And that is something which is the case when this boundary state is annihilated by all the odd charges of the underlying integrable spin chain. And this is a criterion which ensures that the reflection at the boundary of the spin chain is, or the interactions at the boundary of the spin chain are pure reflections. And that's enough to ensure integrability of the boundary state. When that criterion is fulfilled, it can easily be checked to be the case for this boundary state, then one expects that a closed overlap formula exists. And one expects, of course, that it's expressible entirely in terms of beta roots, because this is what characterizes the good conformal operator. In the case that I actually considered, where only one of the scalar operators get a vacuum expectation value, this overlap has actually been derived in a closed form, and it looks like this. You see, it's expressed entirely in terms of beta roots, and these beta roots they actually appear via Baxter polynomials. And there's also a quantity which is related to the Godin determinant, which encodes the norm of the beta eigenstate. So this expression is valid for any operator of the theory, any length, and any combination of scalars. And I should say that it's only non-vanishing if the beta roots are paired in pairs with plus minus signs. Okay, but that's just a tree-level result. In principle, we can now, with our quantized theory, use our perturbative framework to go higher in loop orders. But we expect that we only need the first few loop orders, and after that, one can use an integrability bootstrap method to get the asymptotic result at all loop orders, because that was actually done in a similar setup where one had a codimension 1 defect, which has the same symmetries as this setup here. Okay, that brings me to my conclusion. I hope I've convinced you that magnetic monopoles are fascinating, also in N=4 super young Mills theory. And by solving these beautiful quantum mechanical problems, I actually quantized my theory and provided a novel example of an integrable defect CFT of codimension 3, for which it would be possible to compute the one-point function in a closed form to all loop orders, at least asymptotically. That's all. Thank you.
Thank you very much. Are there any questions? Yes?
Okay. Hi, this is Jérémy Boutier. I have a naive question. On your slide about the scalar propagator, I notice some sort of similarity between your expression and Bessel kernels which arise in random matrix theory. So I was wondering if there is a connection that I might have missed.
It's true. It looks like a Bessel kernel from random matrix theory. I have not thought about it. It might be worth thinking about. You're right.
Because here on the second line, this is very similar to expression of a Bessel kernel.
Yes, that's true. Yes, one should think about it. That's right.
Any other questions? So if not, we will thank Charlotte again and